everybody, this is Ms. Bufford. This video covers building block 6 of Unit 12 over solutions. Building block 6 covers precipitation reactions. Alright, your learning goals for building block 6 are to be able to predict the products for double replacement reactions and use the solubility rules to determine if a precipitate will form during a reaction. So precipitation reactions are types of reactions or types of double replacement reactions where solid products are formed. So what happens here is that we have two solutions that contain ions, and when those solutions are mixed, we have the formation of a solid product, and you can tell that a solid is being formed because the solution will become cloudy and it may change color. A lot of times if the solutions are colorless, you can see in the picture over here to the side, we're mixing two clear solutions and we're getting this white cloudy substance. In order to be able to tell what the identity of that solid product that's formed is, we're going to have to learn how to do a couple different things. The first thing that we need to know how to do is to be able to take an equation with two reactants and rearrange those reactants to be able to predict the products. And then we need to be able to use the solubility rules to determine the solubility of the predicted products. And in the previous building block, we did learn how to determine the solubility of compounds using the solubility rules. So really in this building block, we're learning how to predict the products for double replacement reactions, and then we're going to apply what we've learned about the solubility rules to determine whether or the identity or even just if a solid product is formed from a double replacement reaction. And so let's take a little bit closer look at what's going on during a double replacement reaction. And these beakers up here, the first two beakers, both have ionic substances dissolved into them. If you look up above the beakers, it shows you a picture of what that solid substance would have looked like of 1 unit of that solid substance. When we put that into water, those ions dissociate from one another and they float freely and independently within those solutions. So in this first beaker, I've got the positively charged purple ions and the negatively charged yellow ions. And then in the second beaker, I've got the green positive ions and the orange negatively charged ions. Okay, so if I was to mix these two beakers together, then it would look like the third beaker. And it just so happens that when the purple ions in the first solution came into contact with the negatively charged orange ions in the second solution, they held together, and the force of attraction between those two ions was stronger than water's ability to redissolve them. So that they formed an insoluble product. That compound right there is not soluble. And so what it's doing is it's precipitating out of solution. And eventually all of these particles with the purple and the orange would settle down to the bottom of this beaker. And then occasionally a green particle will come into contact with one of the yellow ions, and they might temporarily form a compound, but the compound that they form is soluble in water, meaning water can dissolve it. So they're just going to come back, be dissolved right back out. And so they're going to stay in aqueous solution, okay? So if ions come together and they stay together and they're forming an insoluble solid, and if they are dissolved again after they come together, then they're insoluble, all right? All right, so let's go ahead and take a look at some examples. Okay, so in this video, we are going to do a couple of examples of the double replacement precipitation reactions. So what we're going to do first is we're going to determine what two products could potentially be formed from each of these reactants. And then we're going to use the solubility rules to determine whether they are going to be soluble in aqueous solution or not. All right, so I'm going to come up here. And the first thing that we want to keep in mind is that these are all in aqueous solution. And when we have an ionic compound that's been dissolved in aqueous solution, those ions are going to dissociate from one another and form independent positive and negative charges in that solution. So For example, I'm going to end up with silver ions and nitrate ions. Nitrate has a -1 charge, and since I know there's only one nitrate attached to each silver, that means silver is going to have to be equal and opposite in charge. So silver is going to be a +1 ion. And the reason I had to reason it out like that is because that is a transition metal. There's no way to look at the periodic table and know exactly what the charge of silver is. All right, and now potassium bromide is going to dissociate into positively charged potassium ions and negatively charged bromide ions. And so the next step, now that we've got all of these broken down into the ions that are floating around in the solution, is I like to just say I'm going to switch the positives. So this potassium ion right here is going to come over and it's going to pair up with that nitrate ion, and silver is going to come over here and it's going to pair up with bromide. So I'm going to go ahead and write my new products. I'm going to end up with silver with a +1 charge. And rather than writing out my formulas, I'm just going to list the ions with their new partners. One mistake that I see students make a lot is that they just automatically carry over all the subscripts, and that's not necessarily always going to give you the correct answer. When you do that, you want to go ahead and balance your new formulas using their charges. So I'm just going to list out the ions with their new partners in this case, and then we're going to go through and make sure that the formulas will balance. And then I have potassium +1 pairing up with nitrate -1. It is worth noting, though, the only time we do carry subscripts over is when they're part of the polyatomic ion. Okay, so now that I have the ions' new partners paired up with them, I can go ahead and figure out what my balance formulas are going to be. And earlier in this year, we learned about the crisscross method, where we drop the signs and we take those numbers and we crisscross them. However, if the charges are equal and opposite, meaning we've got a +1 here and a -1 here, then we can just drop them all and write the formula because we know they're going to be occurring in a 1-to-1 ratio. So in this case, I'll end up with silver bromide. And the same is true here. I've got a +1 and a -1 here, so I'm going to crisscross those, or I could just drop them since they're equal and opposite and end up with potassium nitrate. All right, so here are my two products that I could potentially form with this double replacement reaction. Now let's take a look and determine the solubility of each of these products. If the product is soluble, then I'm going to go ahead and I'm going to write an AQ after it. If the product is insoluble, then what's happening there is it's precipitating out of solution and forming a solid. And so then I would just use a little S after that for a solid. So let's go ahead. Silver bromide. Bromide is the ion to look for in the solubility chart because it has the negative charge. Here's bromide right here. So right off the bat, we're assuming it's going to be soluble, but let's check our exceptions. And there's silver, so this is not soluble because silver is an exception. So because it's not soluble, it's going to form a solid in solution. So I'm going to write S after it. Okay. And now potassium nitrate. So potassium is our positively charged ion, so we're going to look for nitrate in our list. And nitrate is right here. And there are no exceptions, so that means all of the compounds that nitrate form are going to be soluble in water. And since it's soluble, I'm going to say that it's going to remain in aqueous solution. So even if these particles come into contact with one another in water, when they're dissolved as ions, then they're just going to come right back apart because the product they form is soluble. And so they might bump into each other and temporarily form a product that's just going to dissolve right back out into water, and that's why they won't precipitate out. But silver bromide here precipitates out because the force of attraction between this silver ion and this bromide ion is stronger than water's ability to redissolve it or to dissociate it again. So the bond between silver and bromine here is very strong, okay, or it's a very strong attraction. All right, so now let's go ahead and do the second example here. I have sodium hydroxide in aqueous solution. So I end up with sodium ions and hydroxide ions. Hydroxide has a -1 charge, sodium is +1. And then magnesium is going to dissociate into magnesium +2 ions and chloride -1 ions. Okay, so remember I just need to list one of each type of ion that I have. And now I want to switch my positive, so magnesium is going to come over here and pair up with hydroxide, and sodium is going to come over here and pair up with chloride. So let's go ahead and write our new products, or the new ion pairs. So I have sodium with a +1, chloride with a -1, and then I have magnesium with a +2, and hydroxide with a -1. Okay, and since these are equal and opposite, I end up with sodium chloride, just like that. 1 to 1, they're going to cancel each other out. And then for magnesium hydroxide, this too is going to crisscross down to be behind this hydroxide right here. And since this is 1, this crisscrosses down here. So that just tells us we have 1 magnesium. And I have to put hydroxide in parentheses because I have more than one of them. That shows me that I have 2 entire hydroxide groups. And there we go. There's our products. Now let's use the solubility rules to determine whether these are soluble or insoluble. So let's do sodium chloride first. Chloride is the negatively charged component here. So I have chloride right here. And sodium is not an exception, so we say this is soluble. And if it's soluble, it's going to remain in aqueous solution. So it's going to be aqueous. And then magnesium hydroxide. So let's see, we're looking for hydroxide because that is the negatively charged portion of that compound. Here's hydroxide right here. And we need to look and see if magnesium is actually an exception. So yeah, it's not ammonium, it's not an alkali metal, it's an alkaline earth metal. It's not calcium, strontium, or barium, so there's no exception. This compound doesn't meet any exceptions, which means it is insoluble. And so this is going to form a solid that precipitates out of that solution. So our 2 solids that are formed, we've got this one from this product, or from this reaction, and this one from this reaction. There's our products that are actually the solid products that are formed. All right. If you have questions about this video or about this process in general, you're welcome to email me. My office hours, again, they are 10 to 11, Monday through Friday. You're welcome to message me on It's Learning if you need to. Have a good